one more to talk about before we can pull it all together. And I'm reminding you that simply binding the enzyme tighter is not going to work. And making the enzyme work faster on the enzyme, again, is not going to necessarily work. So let's take a look at the next one. Now we need to do some more concepts. First is the transition state. The transition state is a fleeting and unstable stage between the substrate as it's converted into product. It's characterized by distorted bond angles and bond lengths, and it cannot be detected or isolated. So this is an invisible transition. How do we know a transition state is present? Since we can't see it, how do we know? Well, the idea is if I'm going to go from this side of the room to the other side of the room, somehow I had to cross over unless I'm Star Trek and I get transported by the super efficient transport mechanism. So obviously this is the product, and over here is the substrate. Then I had to pass across from it. And that has to be, there has to be a transition state between, otherwise I'll be sliding back and forth very easily. So it has to be present, even though I cannot see it. It's not like an intermediate, because if I was an intermediate right here, so I could walk over, and then I would just stand right here, I'm an intermediate. I'm either the substrate or the product. But now I go over and I walk the product. So there's an intermediate in between. And by the way, there's two transition states to go from the substrate to the intermediate and the intermediate to the product. So there's always going to be one more transition state in each of the intermediates. Another thing we need to talk about is the transition state analog. And this is a stable molecule. It's not reactive, which resembles a transition state. So let's take a look at an example of this. All right, so now what we have is a substrate over here. And what's the critical thing? We've got a phosphate group, methylene group, carbonyl oxygen, and we have an R group sitting out here. Transition state, we assume, remember it's always in the substrate, we assume that it goes in like this. Now we look at this carbon, how many bonds do they have now? That's not normal, is it? But take a look at this, you can see that's going to be distorted as well. So it follows the definition of transition state. The transition state analog, notice they have the phosphate, methylene, methylene. The transition state analog has got the phosphate, the methylene, and now we have a carboxylic acid functional group. This is not going to do any chemistry. Stable molecule. We add it to the enzyme, it's not going to be converted into anything else. However, notice that this matches this matches this partial double bond matches this partial double bond, same atom. The only difference is this is now an oxygen instead of a carbon. So the idea is this sort of looks like the transition state that we propose. Again, we never know for sure what the transition state is like. When we have the proposal, this is what it might be. So there's two experiments that we can do. First of all, if we make transition state analogs, and we then challenge the enzyme and the substrate with it, we found out many times these make excellent inhibitors. Of course, pharmaceutical companies are very interested in that because that's a way of inhibiting an enzyme reaction that we want to slow down for some medical reason. The second thing is antibody enzymes. So this will take a little bit of talking about. If I take a transition state analog for a particular reaction, and I put it into an animal such as a mouse, and I mix in some irritants so the mouse makes antibodies. The mouse makes antibodies against the transition state analog. I can isolate the antibodies, purify it, and I can test it and show that the antibody binds to the transition state with a pretty good affinity. Nothing surprising about that. What's surprising is I take this antibody, all it does is designed to bind to the transition state. What I'm going to do is challenge it with a substrate. And lo and behold, the antibody is capable of catalyzing the substrate, which is not what the antibody is supposed to be able to recognize, into a product. The only thing the antibody can do is to bind to the transition state analog, and by inference, bind to the transition state. Wow. Maybe enzymes are designed to bind to transition states, not necessarily to substrates or products. That's an interesting concept. That's a hunch. Okay, so what we're going to conclude from this is that enzymes are designed to bind tightly to transition state and stabilize the transition state. Otherwise, there wouldn't be any binding. If I stabilize the transition state, that automatically decreases the activation energy, because anytime you stabilize something, you decrease its energy. And therefore, it should make the enzyme go faster. So let's go through some definitions. First is acid-base catalysis. This is a type of mechanism where a proton is transferred. These empirical words, transferring a proton from what? From substrate to substrate, a substrate to an enzyme, or an enzyme to a substrate. All three different ways. It is not the transfer of a proton within the enzyme itself. I'm not saying that's acid-base catalysis. It just has to involve the substrate in some fashion. The next definition involves covalent catalysis. In this particular case, we're going to form a covalent bond, typically between the substrate, or the substrate and an enzyme. And it does not involve the proton. This is not. This is a bond that's being formed. Nothing has to be transferred in the process. All we do is form a bond. Finally, we have intermediate formation, which is going to be a mechanism involving formation or having intermediates between the transition from the substrate to the product. The next one is going to be the proximity effect, which involves limiting the rotation, movement, and orientation, which is the same as saying solution rotation of the substrate with respect to each other or to the enzyme itself. And then finally, we have the transition state stabilization, which is an increase of interaction between the enzyme and the transition state, which thereby lowers the activation energy and increases the rate of the reaction. So we have, in summary, what can we do? We can provide a different mechanism, either acid-base or covalent catalysis, but still providing a different mechanism. We can have intermediates in the process to make the mountains, and break it up into smaller mountains. And then we have the proximity effect and the transition state stabilization. From a numerical point of view, these last two components will provide the biggest increase in rate. However, to do that, we need to many times have intermediates and involve acid-base or covalent catalysis. So they're all going to work together, but the major contributors are going to